Part 3 of the study guide. Protein-ligand interactions can be described quantitatively. O2 must bind reversibly. Reversible binding of a protein P to a ligand L can be described by the equation shown. P plus L is in equilibrium with PL, where Ka equals the concentration of PL divided by the concentration of P times the concentration of L. And this is equal to Ka over Kd, where Ka and Kd are rate constants. Ka is the association constant that describes the affinity of L for P in units of molar inverse. A higher Ka means a higher affinity. Ka equals the ratio of the rates of association, Ka, to dissociation, Kd, to the rates of the forward reaction and the reverse reaction. A reaction is first order if it involves one molecule, such as Pl is in equilibrium with P plus L, but is second order if it involves two molecules, such as P plus L is in equilibrium with Pl. In first order reactions, the rate constant Kd has units of second inverse. In second order reactions, the rate constant Ka has units of molar second inverse. The ratio of the concentration of Pl to the concentration of P is directly proportional to the concentration of L. When the concentration of L is greater than the concentration of P, the concentration of Pl effectively does not change the concentration of L. The concentration of ligand remains constant. Y describes the fraction of ligand binding sites on the protein that are occupied by ligand, and it is a hyperbolic function of ligand concentration. In other words, the fraction of ligand binding sites occupied approaches saturation asymptotically as the concentration of ligand increases. The ligand concentration where half of the available binding sites are occupied, Y equals 0.5, corresponds to 1 over Ka. More often, Kd, which is 1 over Ka, is considered. Ligand concentration equals Kd, where Y equals 0.5, and Kd has units molar. The equation reads Y equals ligand concentration over ligand concentration plus Kd, such that for 90% of available ligand binding sites to be occupied, ligand concentration must be 9 times greater than Kd. The more tightly a ligand binds to a protein, the lower the concentration of ligand required for half of the binding sites to be occupied, and thus the lower the value of Kd, because Y equals 0.5 when ligand concentration equals Kd. Example: protein A achieves half saturation when Kd equals 2 micromolar. Protein B achieves half saturation when Kd equals 6 micromolar. Because A is half saturated at a lower Kd and thus a lower ligand concentration, it has a greater affinity for the ligand. For the binding of O2 to a protein, the equation reads Y equals PO2 over PO2 plus P50, where P50 is Kd when Y equals 0.5. Protein structure affects how ligands bind. The binding of a ligand to a protein is not as simple as the above equation suggests, because there are other factors. A free heme molecule binds carbon monoxide 20,000 times better than it does O2, but a myoglobin-bound heme binds carbon monoxide only 40 times better than it does O2. So the equation is not all that simple, because you have to account for the rest of the protein structure. A myoglobin-bound heme has a greater affinity for O2 than does a free heme because of the distal histidine, histidine E7. How does this work? An FeO2 complex is much more polar than an FeCO complex because 1, the oxygens partially oxidize the iron, leading to a partial negative charge on the oxygens. 2, the partially negative oxygens are stabilized by a hydrogen bond with the imidazole side chain of histidine E7. Therefore, O2 is more stabilized when histidine E7 is present. 4, Therefore, O2 is more stabilized in a myoglobin-bound heme, 500 times more stable than in a free heme, which is the difference between 20,000 and 40. The binding of O2 to a myoglobin-bound heme also depends on molecular motions, or breathing. The amino acid side chains of the protein engage in rapid molecular flexing, thus creating transient pathways in the protein through which O2 can move. Computer simulations indicate that there are multiple such pathways. The distal histidine, histidine E7, acts as a gate, and when it rotates, it can allow the O2 to enter into a pocket in the protein. In other globins, for example neuroglobin and cytoglobin, histidine E7 is directly coordinated with the heme iron, and O2 must displace histidine E7 in order to bind, and histidine E7 returns after O2 has bound. Hemoglobin transports oxygen in blood. Most oxygen carried by blood is bound and transported by hemoglobin in erythrocytes. Erythrocytes are formed from stem cells called hemocytoblasts, when these stem cells produce daughter cells that create large amounts of hemoglobin and then lose their organelles. Therefore, erythrocytes are technically just incomplete cells, and they survive about 120 days. Oxygenated blood releases about 30% of its oxygen into tissues. Arterial blood is about 96% saturated. Venous blood is about 64% saturated. Myoglobin is an oxygen storage protein because it is a monomer, whereas hemoglobin is an oxygen transport protein because it has multiple subunits, that is, it is multimeric, and O2 binding sites. Monomeric proteins are insensitive to small changes in ligand concentration, whereas multimeric protein can be very sensitive. Furthermore, in a multimeric protein, subunits may interact with each other to cause conformation changes, which alter protein affinity for oxygen in response to oxygen demand. Hemoglobin subunits are structurally similar to myoglobin. Hemoglobin, Hb, is a roughly spherical tetramer with 4 heme prosthetic groups. It contains 2 alpha chains and 2 beta chains, making it an alpha-2 beta-2 tetramer. The 3D structure of the alpha subunits and beta subunits are very similar. Their 3D structures are also very similar to that of myoglobin, even though their amino acid sequences are mostly different. The heme binding pocket of the alpha and beta subunits consists largely of the E and F helices. The alpha subunit lacks the short D helix. Hemoglobin quaternary structure involves strong interactions between unlike subunits, alpha-1 beta-1 and alpha-2 beta-2. Each have over 30 residues holding them together. Alpha-1 beta-2 and alpha-2 beta-1 each involve 19 residues. The major stabilizing factors are the hydrophobic effect, hydrogen bonds, and ion pairs, salt bridges. Hemoglobin undergoes a structural change on binding oxygen. Hemoglobin has a T state and an R state. T means tense, R means relaxed, because T state is stabilized by more salt bridges, mostly in the alpha-1 beta-2 and alpha-2 beta-1 interface. The T state is naturally more stable, so it does not require oxygen, making it the predominant conformation in deoxyhemoglobin. In fact, when O2 does bind to T state hemoglobin, it changes to become R state. In order for this to happen, the alpha-beta subunit pairs slide past each other and rotate, narrowing the pocket between beta subunits and breaking salt bridges, and forming new ones. In the T state, the porphyrin ring of the heme is slightly puckered, such that the Fe2+ protrudes slightly towards the proximal histidine, histidine F8. When O2 binds, the heme assumes a more planar conformation, shifting histidine F8 and the F helix, possibly helping trigger the transition from T state to R state. See figure 511 below. Hemoglobin binds oxygen cooperatively. The partial pressure of O2, PO2, in the lungs is about 13.3 kilopascal, and in the tissues about 4 kilopascal. A protein that binds too tightly in the lungs will not release into the tissues. Too loosely in the lungs will not carry enough to the tissues. Myoglobin binds too tightly, illustrated by its hyperbolic binding curve. Hemoglobin solves this problem by transitioning from the low state or from the low affinity T state to the high affinity R state as more O2 molecules bind. This gives hemoglobin an S-shaped sigmoid curve. Myoglobin cannot produce a sigmoid binding curve because it is monomeric. Conversely, the first O2 that binds to T-state deoxyhemoglobin, although it binds weakly, it increases O2 affinity in adjacent subunits. The fourth O2 molecule binds to a subunit already in the R state, thus with much higher affinity. An allosteric protein is where the binding of a ligand to one site affects the binding properties of another site on the same protein. So, hemoglobin is an allosteric protein, and the ligand O2 is a modulator and an activator, not an inhibitor. Allosteric binding may be homotropic, the normal ligand and the modulator are identical, or heterotropic, the modulator is abnormal. The sigmoid binding curve indicates cooperative binding, where the binding of one ligand affects the affinities of other binding sites. The first O2 enables more sensitive response to O2 concentration. Cooperative conformational changes require certain parts of the structure to be unstable, or else no structural changes would occur. Cooperative ligand binding can be described quantitatively. The log of y over y sub 1 minus y equals n times the log of the concentration of L minus the log of Kd. And this is the Hill equation. Plotting the log on the y-axis and log of concentration of L on the x-axis creates a Hill plot, where the slope is n sub h, the Hill coefficient, which describes the degree of cooperativity between binding sites. If n sub h is 1, then the sites are not cooperative. If n sub h is greater than 1, then cooperativity is positive. The upper limit is nh equals n, which has never been reached. If nh is less than 1, then cooperativity is negative. This is rare. Two models suggest mechanisms for cooperative binding. There are two models for the mechanism of T to R state transition, or the reverse. Concerted model, MWC model. Subunits are functionally identical, each subunit can exist in at least two conformations, and all subunits undergo transition from one conformation to the other simultaneously. In other words, no protein has subunits in different conformations. Or the sequential model, KNF model. Ligands are added sequentially. This model proposes more potential intermediate states than the concerted model. And we'll pick up again in a bit.